Question 26 reads, tritium has a half-life of 29.3 years. How many days will have elapsed when the number of radioactive nuclei of a tritium sample has decreased to 10% of its original value? So this problem, there's actually a few things that you need to do. But the first thing that we want to do is we want to get all of our units the same. So that means that if we're ultimately looking for days in our answer, we want to convert the half-life, the known half-life of 29.3 years to days. So that's what I've already done here. I have 29.3 years times 365 days is equal to 10,694.5 days. And then so the next thing that I want you to consider is the equation that we're going to use. So if we're ultimately looking for time, and we know the amount that we know the number of radioactive nuclei that it's decayed to, or that's left, and then we know the number of radioactive nuclei that we started with, and then we can also calculate our decay constant. And so this is the equation that we're going to use, but first we need to calculate our decay constant. So to do that, there's another equation that we can use, and that is that the T half-life, the time for half-life is equal to ln 2 natural log of 2 over the decay constant. And so we know that our half-life is 10,694.5 days, so I can actually plug that in. So 10,694.5 days is equal to natural log of 2 over wavelength, or decay constant. So now I just multiply the decay constant across, divide natural log of 2 by 10,694.5 days, and then I will get a decay constant of 6.48 times 10 to the negative 5. And then so now that I know this decay constant, I can plug this into the equation that I have here, and I know the amount that I'm left with. It says that the tritium sample has decreased to 10% of its original value. So one trick that you can do here for plugging in these values, because it's not directly given to us, but we do have the percentage. So what I'm going to do here is I'm just going to take I'm going to plug in for the initial amount of radioactive nuclei. I'm just going to plug in 100. And so the unit doesn't necessarily matter. I'm going to plug in 100, and then I know that at time t, I have only 10% left of its original value, and then so I can plug in 10, because 10 is 10% of 100. So 10 at time of t is equal to 100 times e to the negative, I know my decay constant, 6.48 times 10 to the negative 5 times time. And then so now this is just algebra at this point. I'm going to divide over by 100, so it'll be 1 over 10 is equal to e of this value. And then I'm going to take the natural log of both sides so that I can get rid of the e here. So this will be natural log of 0.1 is equal to negative 6.48 times 10 to the negative 5 times t. And then so if I plug in the natural log of 0.1, I'm going to get, oh, sorry about zooming in there, I'm going to get negative 2.3 is equal to negative 6.48 times 10 to the negative 5 t. Divide across, and the time t that I'm left with is 35,500 days. So the answer to this problem is going to be D.